Hello, hi, welcome to another video. Today we are going to discuss about power factor in electrical systems. This is one of the most confusing concepts in power system. We were able to understand the terms like voltage, current and power as the concept is clear and it can be visualized easily. But still, power factor remains to be one of the unknown terms in power system. The reason is that we were not able to visualize the concept. In this video, I am not going deep into the electrical concepts. Instead of that, I'll try to clarify the concept of power factor and its compensation through simple examples. I will be explaining power factor and power factor correction by answering some of the frequently asked questions related to power factor. The frequently asked questions are: what is power factor? What is active power and reactive power? How do the reactive power component comes in a power system? What is magnetizing current? How power factor can be corrected? Actually, what a capacitor does in power factor correction, and how to size a capacitor for power factor correction. First, we are going to see what is power factor. As the name speaks, it represents the factor of power. To explain this, we need to discuss another three more terms. What is active power, reactive power, and apparent power? I will take the help of an analogy to explain this. Consider I am going to a tea shop and buying one cup of tea. Okay, my tea will look like this. As you can see here, only 70% of the glass contains tea, whereas 30% is froth. I am spending rupees 10 and I am getting value for rupees 7 only. Whereas 3 rupees is taken by the froth. I won't find this beneficial to me, right? So what will I do now? I will ask the shop personnel to increase the quantity of tea instead of froth. Now I will be getting value for my money with minimum froth and maximum tea. This is the same case with power factor also. Now let's see active and reactive power. Active power is the actual quantity of power used for the operation of an equipment, which is the actual quantity of T in our analogy. Reactive power is the power used by the inductive loads to magnetize and to maintain the magnetic field in inductive systems, which is same as froth in our analogy. We won't be able to make use of this power as it is a wasted component. Apparent power is sum of active and reactive power, which means the total quantity of power drawn from the system. Coming to our analogy, it is the total quantity of the tea and the froth in the glass. It is equivalent to the apparent power. Now, we are in a position to explain power factor. This is the factor of power which is expressed by the formula active power divided by apparent power, which expresses the efficiency of the power consumption in a power system. Larger the power factor, larger will be the efficiency of the system. Normally, the power factor will be varying its value from 0 to 1. 1 means the entire power drawn from the system is completely used for producing the energy, which is in ideal condition. Now let's discuss about reactive power. What is reactive power? Reactive power is the unused power component in a system which is used by the inductive loads for its magnetizing purposes. Reactive power can also be interpreted as a wattless, magnetizing, or a wasted power, and it represents the extra burden on the electricity supply system. A poor power factor is generally the result of an inductive load, such as induction motor, power transformer, ballast, luminaire, welding set, or an induction furnace. Induction motors are the most common inductive load what we are using in power system. I have already discussed why an induction motor is drawing high current from the electrical power system, correlating the technical terms. For those who haven't watched the video, I'll put the link of the video in the description box. An inductive load requires magnetic field to operate, and in creating such a magnetic field, the current will be out of phase with the voltage, which means the current will be lagging the voltage. It can be explained as the magnetizing current, which is essential for setting up the magnetic field in the air gap of the motor. Without magnetizing current, the magnetic field cannot be generated and the motor operation is not possible. The stator winding is inductive in nature, and when an AC voltage is applied across the stator, the current will be lagging the voltage. Now the next question comes: how the power factor can be corrected or compensated? As we have seen in our analogy, we have added more tea to the glass to compensate for the froth. Like that, I need a bottle of electrons, that is a bottle of current, to add into the power system. A capacitor is a container of electrons. In electrical power distribution, capacitor banks are used for power factor correction. These banks are needed to counteract the inductive loading from devices like electrical motors and transmission lines. and it will make the load appear to be mostly resistive. In a sense, power factor correction capacitors increases the current carrying capacity of the system by adding the capacitor banks. You can add additional load to the system without altering the apparent power. Actually, what a capacitor does is, it will store charge from the system and will be delivering the current as required when the inductive loads are utilizing the currents for magnetization. Now, most modern controllers are available at the market which will be monitoring the power factor of the system and will be enabling the automatic switching on and switching off of the capacitors as required. Also, these controllers are capable of monitoring the charge on the capacitors. Now let's see the example of sizing of a capacitor bank for power factor correction. Consider a plant having transformer 500 kVA and it's loaded to 450 kVA with a power factor of 0.75. It will be drawing a current of 626 amps at 415 volt, which means actual power is 337 kilowatt and reactive power will be 112.5 kilowatt. Now let's see a situation where the plant capacity need to be increased by 30%, which means the output power will be 440 kilowatt. How it can be solved? At present, the transformer is already loaded to 450 kVA, which means 90% of the full load capacity. So, any further loading on the transformer will not be possible. So, the next option is to go for the higher rating of transformer, which will not be a practical solution. Then what we can do? We can increase the power factor of the system. To deliver 440 kilowatt, we shall improve the power factor by adding capacitor banks. Initially, we had a 0.75 power factor, and now we are planning to increase the plant capacity by 30%. So we need to improve the power factor to approximately 0.98. The required KVR of the capacitor bank can be calculated by the formula KVR required equal to P into tan power factor 1 minus tan power factor 2. In our case, the angle of power factor 1 and the power factor 2 are calculated and it's arrived as 41.4 and 11.47. Now coming to our case, KVR required is equal to 450 into tan 41.4 minus tan 11.47, which will come as 306 KVR. This means that if you are able to add a capacitor bank of 306 KVR into the system, then we can increase the capacity of the plant by 30% of the initial capacity. This was all about power factor and the correction of power factor. Hope the video was informative, and if you liked the video, please like and subscribe my channel for more informative videos. Thank you for watching the video. Thank you.